Associate Professor at the University of Durham, and as a member of CHESS, the society, the Centre for Humanities Engaging Science and Society, which is hosting this series. So Peter has recently published some work on the search for extraterrestrial life, and the paper today is going to continue that theme. He's going to be talking to us about whether enough high-risk, high-reward space science projects are being funded. Peter.
Thanks a lot, and thanks everyone for coming. I don't know, everyone is so busy with things these days, and it's hard to fit things in. So it's great to have so many people here. I've been thinking about this topic for a couple of years now, and in particular the question of astrobiology. But the basic question about these high risk, high reward, or so-called projects or missions can be applied much more widely to space science more generally, or even to science more generally. But I do think particular issues come up in the context of space science and astrobiology. So that's going to be the focus. But a lot of these issues do go a lot wider. This is going to be based on this paper that's now come out in the International Journal of Astrobiology, but just preparing for this talk made me think about things in a new way. So this is the first time I've given the talk quite in this way, and it goes a little bit beyond the paper. But also there's a lot more in the paper as well, if anyone's interested. So let me just start with a synopsis of the talk, and this is basically an argument. The projects or missions that fail, quote marks, are embarrassing. So I'll talk about what fail means. So that's a premise. High risk projects will fail fairly often, and this is more or less how I'm going to define high risk projects. So I'll say more about that. There are plenty of interesting projects and missions that will almost certainly succeed, giving funders every reason not to fund any high-risk projects. So as a funder, you want to see success, and if you're being given lots of interesting projects and missions, then it's going to be tempting just to fund the safe ones. So some high rewards, I think would only be accessible via high-risk projects. So it's not like every high reward that's out there in science is accessible by low or medium risk projects. So sometimes you would have to take a risk to get a particular reward. And yeah, so if those premises are roughly right, then perhaps we can conclude that some high rewards will forever escape us. But perhaps that's okay. So that's basically the synopsis, and I'm going to run through these premises more or less and explain what I mean a bit more. So this is something that NASA and the National Research Council in the US is conscious of. This thought that high risk projects are prone to failing, and increased government and public scrutiny make projects that fail increasingly untenable. So this can be found in this enabling foundation for NASA's Earth and Space Science mission. So people in the business are certainly conscious of this, and this is an important definition of a high-risk project. Is a project that has a chance of failing in a given sense. And obviously, if that does happen, people are going to look at that wasted money and ask what happened. So what do we mean by projects that fail? I think an interesting example is Gordon Walker's 12-year search for exoplanets from 1980 to 1992. So this was funded by NSERC, Canadian Research Council. And Walker's team did get a publication out of it in 1995. And here's some of the key quotes. We have carefully monitored the radial velocities of 21 bright solar-type stars for 12 years. None has shown any reflex motion due to a substellar companion. So no planets have been discovered, in other words. And he says in this paper, when we began this program over 14 years ago, we fully expected that with sufficient precision, we would find several candidate giant planets. So this last quotation here sort of explains, I think, why it was funded. I think Walker and his team were able to convince the funder that this really wasn't a high-risk project, that there was every reason to suppose that at least some candidate planets would be uncovered, but that wasn't the case. It was a null result after 12 years. So this is the sort of thing that we might call a project that failed in the relevant sense. So there's a sense in which it didn't fail. I mean, it explored the chosen parameter space, and by exploring that parameter space, it made other people think in different ways about why has this project failed and what might we do differently next time. But it did fail in an important sense. In the final scientific payoff was of limited significance compared with initial ambitions. That's roughly the definition of failure that I'm working with here. So that's the kind of project that is high risk, one that might fail in that sense. I think the definitions surrounding this debate are really important. If we get the definitions wrong, we might think that high risk, high reward projects and missions are being submitted and funded when in fact they are not. So we've got to think carefully about these key terms. And in fact, I think this has happened in NASA itself. I think they have misdefined one of these key terms, and that has led to some people thinking that high risk, high reward projects are being submitted and funded when they're not really. So let me expand on that. So this was a publication from the National Academy of Sciences. And in this publication in 2017, there was a specific recommendation aimed at NASA saying that NASA needs to investigate appropriate mechanisms to ensure that high risk, high payoff fundamental research and advanced technology development activities receive appropriate consideration due to the review process. So there was a worry hanging around here that these weren't being given enough consideration, these sorts of proposed projects, high risk, high payoff, and NASA ought to do something about it. So there was an investigation that took place as part of this funding opportunity called the Research Opportunities in Space and Earth Science in 2017. And a survey was conducted during this funding competition. There were 1,577 proposals submitted, and peer reviewers of these proposals were asked a question which was supposed to identify any high-risk proposals. And the question was, to what extent would this proposal test novel or significant hypotheses for which there is scant precedent or preliminary data, or which run counter to the existing scientific consensus? And 10% of the proposals were flagged, and out of these, 35% were funded, compared to an overall selection rate of only 24%. So the conclusion coming out of this was that enough high risk, high reward projects are being proposed, so 10% in this case, and they were more likely to get funded than other proposals, and it was a 35% chance rather than overall 24%. So this led some in the community to say that that this was Paul Hurt speaking in 2018, based on this survey, that it's a myth, he said, that high risk, high impact projects aren't being submitted and funding. They've conducted the survey and shown that they are being submitted and they are being funded. And I think there's a worry about this definition, which it all hangs on really. Whether they get counted as high risk depends entirely on whether they meet this definition according to those peer reviewers who were put in charge of this. So something funny is happening. Okay. So note that on this definition, if the proposal tests a significant hypothesis and there is scant precedent, then it comes out as high risk. And what I'm going to suggest is that it's quite easy to think of a project or proposal that tests a significant hypothesis and there's scant precedent for it, but you wouldn't want to call it high risk. And so let me suggest one example. There might be better examples out there, but this is one example that I think a peer reviewer might have thought met this definition that they were given, but that isn't really high risk in the relevant sense. So the example I've chosen
we can't see your slides any longer. Is that deliberate?
Oh no! Oh, hold on. Yeah, it's because I had that problem. Thanks for mentioning that. So. Is that better?
Yeah, we can see them now.
Yeah, they're back. Yeah.
Yeah, okay, thanks. So there's this Nancy Grace Roman space telescope. This is named after Nancy Grace Roman, who was the first chief astronomer for NASA, who died in 2018. This was previously called the W-FIRST telescope, and it's due for launch in 2025. And it's going to conduct a micro-lensing survey. So it looks for planets that are lensing the light from a star, and the view from Earth, as you can see on the right there, as that planet passes directly in between the Earth and the star, there's sort of a lensing effect on the light from the star that can be picked up. So this will be the first major survey of its kind. When it was first proposed, there was very little precedent. So I think this could easily be called a project for which there was scant precedent and which tests a significant hypothesis. And so it would have met the definition that those peer reviewers were given. But I think we fully expect this project to deliver exciting results based on some solid theory behind it. So I think the probability of it failing, coming up with a null result in the way Gordon Walker's project did, is extremely low. And if that's correct, then it shouldn't actually be categorized as a high risk project, I think. But even if you don't like the example, the basic point is that I think that there's plenty of conceptual elbow room to match up the Rose's 2017 survey definition with projects that are not high risk in the relevant sense, where they could fail in the sense that the final payoff is lacking or greatly lacking in significance compared with initial ambitions, as in the Gordon Walker case. So there's a worry, I think, about that definition. And an alternative question that might have been asked of those peer reviewers would be, assuming the proposed project goes to plan, so there isn't some technical glitch or hiccup or something, what's the probability that the final scientific payoff will be of limited significance, with options relatively high, medium, or relatively low? Something like that. I'm still sort of working on trying to get the ideal question or the ideal definition here, but this seems an improvement to me. And I think if this had been used, then it would have resulted in far fewer of those Rose's submissions being labelled high risk and being funded. So it would have given a very different result. And I think the Nancy Grace Roman Space Telescope microlensing survey does not come out as high risk on this definition. So that just sort of shows that there's the sensitivity to the definition. So that more or less covers the first two premises and sort of clarifies some of the terminology. The third premise, I'm not really going to defend this. I think it's fairly self-explanatory. There are plenty of interesting projects and missions that will almost certainly succeed, assuming no technical problem, giving funders every reason not to fund any high-risk projects. So there were loads of exciting things we could do right now, with our next few $1 billion or whatever. That we're just inundated with exciting possibilities, and the vast majority of those, you might want to say, are not high risk proposals. So I'm going to move on to this final premise. Some high rewards will be accessible only via high risk projects. Again, I'm not going to defend this too much. I think it's reasonable to suppose that some potential rewards could only be accessed by taking a risk. So an example might be if we were to explore an underexplored parameter space, and there were theoretical considerations, but they could only weakly indicate what we might find. Now, suppose there is something really exciting in that parameter space. Well, the only reason we would find it, you might think, is if somebody decided one day there's a parameter space here that nobody's explored, and we might as well take a look. But yeah, you can imagine that might not get funded if it's looked on by funders as a fishing expedition, which has every chance of bringing back nothing. We might find nothing of interest, or we might find something shocking, but we just don't know. It seems that there are surely some parameter spaces out there that will be like that, where we really don't know what we might find. One project may be coming under this heading, under the heading of high risk, high reward, could be the silicon-based life research. Many people think there's a high chance it won't lead anywhere. That silicon-based life is somehow not realistic. But of course, if it did, that would be incredible. So it seems like it's a case of a project where the high reward is only accessible by taking a high risk, and it can't be dismissed entirely. The incredible does crop up in sometimes in science, and we can think of many examples, such as the discovery of continental drift in the 60s was shocking to many, given that they thought it had been proven impossible, and the acceleration of the universe's expansion in the 90s, and giant viruses in the 2000s. So we can imagine some things that are incredible and highly unexpected. So maybe silicon-based life will one day be another such example. I put the silicon-based life into Google Images just to see how exciting it would be, and this was what came up. And also these two examples. So that gives us an idea of the high reward that is potentially out there if we search for silicon-based life. Okay, back to the talk. So if those premises are pretty secure, then maybe some high rewards will forever escape us. But we might think that's okay. We can't go after everything, with limited resources. In particular, we might think it's okay if there were already plenty of high rewards that are accessible via non-risky projects and missions. And I think that is the case in contemporary space science. If we think about 3 target options for the James Webb Space Telescope, which is due to launch later this year, people are really excited about the following 3 options at least. There are many other possible target options for that telescope. So 1, gas giant planets and mini Neptunes. People make the argument that the JWST would be great at looking at these, and we'd learn a lot about the formation of planetary systems. Other people want to look at habitable zone rocky planets, such as those within the TRAPPIST-1 system, which could potentially have surface water. They could be good planets for life. And some people want to look at planets such as K2-22b, which is a disintegrating rocky planet orbiting its parent star once every 9 hours. And we'd see the insides of the planet more or less by watching that planet disintegrate as it gets too near to its parent star. which would be a really cool thing to do with JWST. Now, everyone thinks that these are all high rewards, really. These are all exciting things to go after. And there's no way JWST can do all of these three things, never mind all of the other options. So if someone were to suggest, let's do something risky with JWST, let's look at a target which, you know, might be exciting but also might not, they wouldn't have a hope, really, because there were just too many targets that definitely are exciting for someone to go after a potentially boring target. So what I'm moving towards there, if we consider JWST, is the thought that we should forget about funding high risk projects. Maybe there were just too many projects that can give us high rewards without taking a high risk. And this is how it used to be done, actually, within NASA. The risk assessment policy in 2009 included this: categorize the mission risk rating into one of three categories: high, medium, and low, where a medium and low risk rating is perceived as passing. This is from a NASA white paper from 2009. So in other words, if your project comes out as high risk, then whatever else looks good about that project, it gets thrown in the bin. That's how it seems from what's in this white paper. But that could almost be justified if you know, there's so many exciting medium and low risk projects out there, as there are with the JWST telescope over the next 5 to 10 years, for example. You know, there's no match in science between high reward and high risk. It's, you know, there may be in financial investing, but in science there are many high rewards where you don't have to take a high risk. And if we think about the biggest reward in all space science, well, we could debate what that is, but one of them has got to be the discovery of a pale blue dot, you know, the first direct image of an Earth 2.0, which many people think is sort of on the horizon in the next however many decades. I mean, we know how to make a telescope that can directly image exoplanets, and many people think there'll be a pale blue dot out there somewhere. So, you know, that's going to be a massive moment in human history. And to access that big reward, we don't need a high risk project in the sense that I've defined it. And in fact, all we need to do, and we know how to do this, is create a telescope like the Louvois telescope project, which is a very serious proposal and is sort of billed for launch in the next couple of decades, which would be capable of directly imaging exoplanets. And that's not a high risk proposal, because everybody accepts that if we were to build and launch Louvois and there weren't some tragedy, you know, the technology went wrong or something, you know, if the project just went to plan, then it would generate all sorts of amazing outputs. So that's sort of a low risk, high reward project. But of course, it's really expensive. And some people might say that, hold on, we need to factor in the cost. You know, we shouldn't be just talking about risks and rewards. We should be talking about a relationship between risks, rewards, and costs. And Louvois might well not go ahead simply because it's so expensive that it would put the brakes on lots of other potential missions and projects that could go ahead otherwise. So you might think that what we want really is something like this, where we score projects where the score is higher if the probability of success is higher. In other words, the less risky they are. We score it higher the more significant the payoff, so the higher the reward. And we score it higher if it's cheaper as well. So we divide by the cost. And this is an equation that you can find in that NASA white paper from 2009. As far as I can tell, nobody took paid much attention to that paper. Yeah, if we're dividing by the cost, well, now the Louvois project might not get funded, given the whatever project score comes out of this. And cheap, high-risk projects could get funded. So you can imagine if there's a high-risk project which really doesn't cost very much, then it won't matter so much if it doesn't deliver anything interesting at the end. You know, you explore a parameter space, doesn't really cost you much to do it. You might have found something amazing. Turns out you found nothing of much interest, but nobody minds too much because it didn't cost much. So that's the kind of high-risk project that could get funded if we factor in the cost. In addition, as we've already argued, many high rewards are pursuable, because to pursue many high rewards, you don't need a high-risk project. So what are we ruling out now? What might we never find? Well, projects that are high risk and are not cheap, it's hard to see how they could ever be realistically funded. I mean, in this case, the reward would have to be huge. If we were going to use this equation, or, you know, it's a rule of thumb, really. Obviously, it's not an exact science, so you can't put exact figures into these variables. But if we were to use this equation qualitatively, if you like, then to get a high-risk project that was expensive funded, the reward would have to be huge. But it's hard to see how the reward could be big enough to make it competitive alongside low and medium risk projects and cheaper projects. I think an important consideration here is that in some cases we don't know what we're missing. There are unknown unknowns in science, and in that case, we really can't put any figure on the potential reward. So I think with a case like that, we have sort of a chicken and egg situation, where there might be a project we can never justify funding it without knowing the great significance of the reward. So suppose there is a reward that would come back if we funded this project, but we've got no idea that it's out there waiting for us. In that case, if we only knew how significant the reward was, then we would fund the project. But we can never learn the significance of the reward without funding the relevant project. So this is the kind of case that I think is more likely to forever be lost to our potential access. The unknown unknowns. I think it's helpful to compare two different types of high-risk project here, and I'm just coming to a close here. So I think this is my last slide. So a silicon-based live project, we have some kind of handle on the potential reward. We can say that there's a potential high reward out there, which is exciting, and people want to go after. If we compare that with the exploration of an unexplored parameter space, we really don't know what we might find. And these are both high risk in the right sense, because in both cases, we might come home empty-handed, relatively empty-handed. There's nothing significant at the end of spending all that money. But there's a significant extra barrier to acquiring funding in case two, because it's only high reward in a very thin sense, in the sense that there's a chance of some kind of highly significant payoff. But I mean, that really doesn't count as a high reward project, you might think, because there's always a chance of some kind of highly significant payoff in almost any project. So you can't quite compare these two examples, 1 and 2 here, whereas 1 seems to come out as a high risk, high reward project. 2 is high risk, but to call it high reward, well, then you'd be using the term high reward in just this thin sense. So I think it's whereas you could justify maybe funding the silicon-based live project on the grounds that it's a high risk, high reward project, I don't think you could quite justify funding the exploration of the unexplored parameter space when we really don't know what we might find. So I think that's an important distinction as well. Okay, so that's as far as I got, and there were many unknowns there that I'm still exploring. So any advice is much appreciated. So thanks for listening.
Thank you very much, Peter. So